All right, so here we are with number 6 on the BC exam. Infinite series and Taylor polynomials is always the last thing I cover in a BC class. And, due to the whole global pandemic thing, we didn't get to it this year. Well, we did a little bit, but not all of it. So I'm hoping that this will be helpful as you study for the AP exam this year. So let's take a look at this one. All right, so here we've got this graph and we've got a table and it says function f has derivatives of all orders for all real numbers x. So all that means is this function f, which is this curve function here, means you can just derive it forever. You can take a first derivative, second derivative, third derivative, fourth derivative, and just keep going. And those derivatives are going to exist. And so it says it shows a portion of the graph above along with the tangent line, which is this straight line here. And it's at x equals 0, which just means when they created the tangent line touched the graph f at x equals 0. And selected derivatives of the function are given over here. And that's really important, obviously, because we don't have an actual function for f, which means we can't take the derivatives ourselves. And so they were kind enough to give us some derivatives in this chart. All right, so part A, let's see what we're asked to do with that. First and foremost, we need to write a third-degree Taylor polynomial for f about x equals 0. And that's really what this problem focuses on, is writing Taylor polynomials, which is fantastic because that's one of the things we didn't get to. So hopefully this problem will help illustrate that process and how it works. And the bottom line is that Taylor polynomials is just a formula for you to memorize. And if you know this formula, you're going to be in good shape and you should be able to generate any Taylor polynomial that you need to generate. This one specifically is a third degree. That's what this 3 right here means. It's a third degree Taylor polynomial. And all that means is that you're going to follow this formula out until you take the third derivative of the function. You'll have a 3 factorial in the denominator, and this term x minus c is raised to the third power. So this is where a third degree Taylor polynomial would stop. Now, if you wanted to do a fourth degree, you can just keep going, and you can go for as long as you want. The fourth degree would just be the fourth derivative of your function over 4 factorial times x minus c to the fourth. You could do a fifth degree, sixth degree, etc. You could go on for as long as you want. Now, what a Taylor polynomial does is it approximates the original function. And that's something we've actually done quite a bit of this year. We've just used tangent lines for our approximation. And notice that if you stop right here, if you don't get to the second degree part, all this is right here is the equation of a tangent line. This is your y-intercept, this is your slope, x minus your x-coordinate. So really, you've been doing Taylor polynomials this year. We just didn't call it that. And what you've been doing is a first degree Taylor polynomial. It just stops here where you're taking the first derivative. It would technically be divided by 1 factorial, but that's just 1, so we don't write it in. And then you have x minus c to the first power. So a first degree Taylor polynomial is basically just a tangent line, which we've used quite a bit this year to approximate a function. The thing is, if you want to approximate a function, you can approximate it much more accurately than what a tangent line can do. And you do that simply by extending this to a second degree function or a third degree function. And for every term that you add on, fourth degree, fifth degree, sixth degree, etc., this approximation of f is going to get more and more and more accurate. But for the purposes of this problem, it just wants us to go to a third degree, so this is where we're going to stop. And the way that's going to look then, since we're doing it around x equals 0, that means all of these c values are going to be 0. So this particular polynomial is going to be f of 0 plus f prime of 0, x minus 0. All of those c's are essentially turned into zeros. There's a special name for a Taylor polynomial centered at 0, and that is a Maclaurin series. We'll talk about that later. But if you see that term, which we will see in this problem, it just means a Taylor polynomial is centered specifically at 0. So now, how do we find f of 0? How do we find f prime of 0? Especially since we don't know what f is. Well, that's where this information that they gave us comes into play. So if I need to know f of 0, I look at the graph of f, and when x equals 0, it looks like that y value is going to be 3. To find f prime of 0, I need to know the derivative of this function at 0. Thankfully, we've got a tangent line, and we know that the slope of the tangent line is equal to the slope of f. And it looks like if you go down 2 and over 1, that this tangent line has a slope of -2. and therefore f also has a slope of negative 2 at that point. So we'll substitute negative 2 right here for f prime of 0. X minus 0 would just be x. And then your second derivative, well, they tell you here your second derivative at 0 is 3, so we're going to substitute a 3 right here. It's going to be 3 over 2 factorial. 2 factorial is just 2 times 1. Then you'll have your x squared term. Your third derivative is negative 23 halves over 3 factorial. 3 factorial is 3 times 2 times 1, which is 6. And you'll have x cubed. And so that's what this is showing right here. F of 0 is 3, f prime of 0 is negative 2, etc. And so we're just filling in all those f-zeros and derivatives at 0 using, again, this graph and this chart. Of course, we can simplify a little further. 23 halves divided by 6 will be 23 twelfths. But this is it right here. This is your third degree Taylor polynomial for f centered at x equals 0. And again, this is basically going to do what a tangent line does. It's going to approximate the function. It's just going to approximate it much more accurately than a simple tangent line. The curves of this graph will better match the curves of f, and you'll get a better approximation. So that's the gist. When you're writing Taylor polynomials, you need to have this formula memorized. And as long as you have that formula memorized, then you're just able to take derivatives, plug in y values, plug in the derivatives, and simplify it down to get your Taylor polynomial. Okay, so part B. First, we've got to write the first 3 non-zero terms of the Maclaurin series for e to the x. Remember, this is just, again, it's another Taylor polynomial. It's just going to be centered at 0. And then write the second degree Taylor polynomial for e to the x times f of x at x equals 0. So let's just start with the e to the x part. Again, remember, this is the formula we were using. Now, they didn't ask for a third degree, so we don't have to go all the way out to this term. They're simply saying the first 3 non-zero terms, but we're still using this formula here to generate that. So if you're talking about e to the x, what you need to do then is plug in 0 to your function. So this would be f of 0, which means e to the 0, which is 1. And the nice thing about e to the x is that the derivative of e to the x is e to the x, and the second derivative of e to the x is e to the x. So here, and here, and here, those are all going to be e to the 0, which is just 1. And so that's what we're doing here. You're taking your function e to the x, you're plugging in 0, which gives you e to the 0. The derivative of e to the x is e to the x, and you're plugging in 0, which gives you e to the 0, so on and so forth. And I'm stopping here because this will be 1 term, this will be 2 terms, and this will be 3 terms. And that will give us our first 3 non-zero terms. So of course e to the 0 is 1, so you get 1 here, plus 1 times x, plus 1 over 2 factorial times x squared, and these are the first 3 terms. E to the x is one that I would recommend you memorize. It's pretty simple and straightforward, and it saves you time not having to go through this process to figure out what e to the x is. You can just extend this as long as you want. The next term will be x cubed over 3 factorial plus x to the 4th over 4 factorial, and that's just going to keep going. So e to the x along with sine of x and cosine of x, I would recommend that you memorize those Taylor polynomials, just so on the AP test you can generate those on the spot without having to go through this process. But anyway, here it is, our first 3 terms. Now the next thing they want us to do is take e to the x, which we just found here, and multiply that by f of x, which we generated in part A. And so the way that's going to look is here is the approximation for e to the x that we developed times the approximation for f of x that we developed. And if you want to multiply these two functions, you just need to multiply these two things together. And the way we do that, of course, is distribution. Now, notice it said second degree Taylor polynomial. That means that in our answer, we shouldn't have anything higher than the second power. So when I distribute, I'm going to take 1 times 3, 1 times negative 2x, 1 times 3 halves x squared, and I wouldn't multiply 1 by any more terms because this is an x squared term and that's the highest that we want. Then the next thing I would do is take my x term and distribute, so x times 3 is 3x, x times negative 2x is negative 2x squared, and I would stop there because if I go any further, I'm going to get powers greater than 2, which I do not want. And then I'm going to take my x squared over 2 and distribute that. I'm going to multiply it by 3, which will give me 3 halves x squared. And again, I'm not going to go any further than that because that would give me a cubic term, which is more than we want for a second degree Taylor polynomial. So this is what we just discussed. This is our distribution. And of course, after this, you just want to combine like terms. So negative 2x plus 3x will be positive 1x, etc. And then you combine all the x squared terms, and this is what it simplifies down to. So 3 plus x squared is our approximation for e to the x times f of x. All right, moving on to part C. Now we've got a new function h, and let it be defined by essentially the integral of f, which is the function we've been dealing with, from 0 to x. And we want to use the Taylor polynomial found in part A to find an approximation for h of 1. So first of all, what does h of 1 equal? Well, h of 1, if you plug in 1 for x, would equal the integral of f from 0 to 1. So here I'm integrating from 0 to 1. This is my function f that I'm integrating. And then notice the next step here is just that integral. The integral of 3 is 3x. The integral of 2x will be 2x squared over 2, which simplifies down to x squared. The integral of 3 halves x squared, you just add a 3 and divide by 3, which gives you 1/2 x cubed, and so on and so forth. So all this is right here is the integral of my function f. Now we're integrating from 0 to 1, which means my bounds are right here. I need to plug in 1 and then subtract and plug in 0. The nice thing about this problem, of course, is when you plug in 0 to this function, you get 0, so we don't really even have to worry about that bound. But we're going to plug in 1, which gives us 3 minus 1 plus 1/2 minus 23/48. So of course 3 minus 1 is 2, and 2 plus 1/2 is going to give you 2.5 or 5 halves. And you don't have to simplify this down all the way because technically this is an approximation. That is the answer. But it's not too hard to clean these fractions up. And if you do, you're going to get 97/48. Now, really important here, this is not h of 1. This is just an approximation. If we wanted a better approximation, we could have taken function f, and instead of doing a third degree Taylor polynomial, we could have extended that and kept going and going and going. And if we had done that, then this approximation that we get here would be even more accurate. But this is using that Taylor polynomial from part A. This is our approximation of h of 1. We think it's approximately equal to 97/48. But that's all part C is asking for. They just want you to integrate the function f from 0 to 1. So there you go for part C. All right, part D. If I understand correctly, I don't believe they're going to be asking for error on the shortened exam this year, but it's a pretty simple concept or topic, so we're going to go ahead and go through this anyway. And they say it's known that the Maclaurin series for h, and h is the function we just found in part C, is going to converge for all real numbers. It's also known that the individual terms for h of 1 alternate in sign. I don't know if you guys noticed that in part C. I should have pointed that out. Every term went from positive to negative and positive to negative. So what we have here is an alternating series because the signs alternate. And they decrease. It just means that as you extend h out, your terms get smaller and smaller and smaller, and they're approaching 0. So use the alternating series error bound to show that the approximation found in part C differs from h of 1 by at most 0.45. All right, so if you remember in part C, this is our approximation for h of 1. We just integrated this function here. These are the terms that we got from our integral, and based on those terms, we got 97/48. Now, as I said in part C, this is not h of 1. This is just an approximation of h of 1. So that means there's error. If we knew what h of 1 actually was, and we subtracted our approximation, we would get a difference. There would be some difference between our estimation and the actual value. And a question that we always have is, well, how big is that error? How much is our approximation off by? And in an alternating series, that's actually really easy to find. You know, I said that for f, we could have kept going. We could have had a 4th degree term and a 5th degree term. So we left a lot of terms off here. And it turns out with an alternating series that the most your error can be, so the most we could be off by on our guess of 97/48, is found by simply the next term that we left off. So that x to the fourth term that we didn't use, that x to the fourth term is going to tell us the maximum error that we have in our approximation of 97 over 48. So if we want to figure out what the next term is, that x to the fourth term, we've got to go back to this table because what we're going to need is the fourth derivative of our function. Notice in part A we didn't use that. We stopped at 3. But if you wanted to extend that one more term, you would have to go to n equals 4 and find that fourth derivative. So if we do that, we can determine that the next term of f would be 54, which is our fourth derivative, divided by 4 factorial times x to the fourth power. And again, we get this just using that Taylor polynomial formula that I gave you in part A. So if this is the next term in f, then the next term in h, that term we didn't use, the thing that would come after 23 over 48, we would get that by integrating this term from 0 to 1. So we're going to integrate 54 over 4 factorial x to the fourth from 0 to 1. 4 factorial is 4 times 3 times 2, which is 24, and 54 over 24 will simplify to 27 over 12. And so if we integrate this, we're just going to make it x to the fifth over 5, which gives us x to the fifth 27 over 60 from 0 to 1. You plug in 1, which gives you 27 over 60. Technically, you would subtract and plug in 0, which is 0. And 27 over 60 simplifies to 9 over 40. So, going back to how we approximated h, if we had extended this one more term, that next term would have been 9 over 40. And what that next term, that 9 over 40, represents is the maximum error that we got, or that we could possibly have in our approximation that we found. So again, one more time, if you want to find the error in an approximation that you have found in an alternating series, the error is going to be the next term that you did not use. And so for this instance, for this case, the next term we didn't use would be 9 over 40. That's what would have come next if we had extended this one more term. So what that means is then that your error at most is going to be the absolute value of 9 over 20, which just so happens to be 0.45, which is what they asked for in here. So again, for an alternating series, the error that you have in your approximation can be found by extending that alternating series one more term, and whatever that next term is, that is the maximum error that you could possibly have in your approximation. We use the absolute values here simply because in an alternating series, of course, you can have negative terms. And by error, we're not saying that 97 over 48 was too big or too small by this amount. It could be either one. We're just saying that it is off, at most, by 0.45 in either direction. All right, so I know that was a lot, especially since this isn't something we've covered in class, but hopefully this gives you a decent overview of Taylor polynomials and how to find those and how to generate those. And then once you have generated those, how to work with them. For instance, taking two Taylor polynomials and multiplying them together, which we did earlier. And so this should be a good overview. Whatever questions you have on this, please reach out to me and ask. I'll be happy to cover it in as much detail as I possibly can. I'll probably do a couple more videos involving Taylor polynomials because they're hugely, hugely important in BC Calculus. Definitely something that you should spend some time studying and reviewing. Until then, I'll see you next time. Talk to you later.